This is the CIELAB lecture. We're going to talk about CIELAB, which is the color space that we use to specify color, to figure out how to get to a color, and to decide whether or not we got close enough. Because of that, I think you could argue that this is a pretty important lecture, so pay attention, okay? CIELAB values are a color space, and the color space is very similar to Munsell, the Munsell color space. They are actually based on Munsell, or maybe not based on, but designed to match fairly closely to the ideas that were in Munsell and also the values. So I'm going to argue CIELAB, the greatest thing since Munsell color system. Here we see basically the layout of CIELAB. On the top here we have white, on the bottom we have black. This spine is the neutral gray spine, and as we go around here, of course, we see the color wheel that we're all familiar with. This is 3 dimensions, I should mention, and really it looks like all the other 3-dimensional color spaces that we looked at. The center, that is the spine, is called L star. The position on there tells you where you are in terms of lightness to darkness. It starts out at 0 at the bottom, which is pure black, and it goes up to 100 at the top, which is pure white. This corresponds very closely to Munsell's idea of value, which is our perception of lightness. Another thing about it is that it's more or less linear to the human eye. In other words, a step at the bottom here from 0 to 10 is basically kind of the same size as a step from 90 to 100. Remember this Kodak grayscale card? On the one end over here, it starts out at 0, which is called A, 1, 2, 3, etc., on up to 19 at the other end. This was density units, if you recall. And I remember making a big point of a single little detail. We tried to decide where the middle of this was. And I mean middle in terms of what is halfway between white and black. And we kind of decided that it was someplace around here. Maybe it was the M, which is 7 or something like that. And really, the answer, one way to look at the answer is that this one here, this one that's called number 3, which looks like a very light gray, that one is halfway between white and black. And when I say halfway, I have to explain. What I mean by that is in terms of the amount of light that's reflected. The reflectance of this patch here, which is number 3, the reflectance of that is halfway between pure white and pure black, which is odd. The eye is not a linear device, and L star is designed to match that. And L star is designed to match that nonlinearity. Here we see the formula. It's a little bit ugly. I apologize for that, but it's not my fault. I have it in this spreadsheet here. The spreadsheet is available if you'd like that. Just let me know. Basically, this is the big part of it. It's the cube root function. You may notice that this is in Excel format. I do have the spreadsheet. Ask me for it. I'll probably let you have it. Remember our good friends, the tristimulus functions? Okay, they were the color matching functions that were used to emulate what a color matching device would do. They don't emulate the human eye, they emulate this device. The center one here, the Y bar, that is the function that was used to essentially relate to our perception of lightness. The Y bar function, along with the spectrum of whatever it is that we're measuring, are used to compute the capital Y value, which is then used to compute the L star value. You may have noticed, but I'm guessing perhaps not, but you may have noticed that there is a Y over Y sub n. Let me explain that a little bit because it's an interesting thing. Y sub n is used to normalize against the illuminant. In other words, to make sure that white is white. We have a whole lecture talking about illuminants coming up, and that will be definitely fun. And now, my first tirade. I apologize in advance. there's going to be a few of these. The formula for L star is a bit complicated. Not terribly complicated, but there's all kinds of numbers in it and stuff. It's got this funny thing that if the reflectance value is below a certain point versus above a certain point, you use a different formula. Mathematicians don't like this. The thing is that there is a simpler and a much more accurate formula. Here it is. It's something that I introduced in a TEGA paper in 2015. Simpler formula, and it's more accurate. I introduced it, but really it's based on formulas that have been around for a long time, and my beef with the CIE committee when they came up with this, my beef is that they should have looked at this previous work. End of my first tirade. Now we move on to the second component of the LAB system, the A star value. This you will probably recognize as, or maybe you won't, color opponents. Red and green were the opponents from, who was the name of that guy? I'm forgetting it right now. Let's just go on. A color can be described in terms of either being reddish or greenish. If it's reddish, we give it A star value that is positive, and if it's greenish, we give it an A star value that's negative. It goes up to something like 100 on either end. So this is the, who was that guy? Herring, yes, Ewald Herring. This is Herring's color opponent. This is the A star, the reddish to greenish component. And here we have a measurement of that value. Did I say I was going to give some tirades? Well, here's my second one. The second tirade is based on a paper that I published in Color Research and Application a little over a year ago. It's a minor one, but it could be it could be a source of confusion for some people. So let's go through it. The A star axis, I called it in that last slide, I called it red versus green. And I gotta tell you something, that's not exactly true. You will find that if you Google CIELAB and read any explanation of it, you will find that it's called the red axis, but it's not red. Everybody calls it red, but it's actually the magenta axis. Magenta versus green. And the reason why this happens, CIELAB is based on Elliott Quincy Adams, the color space that he came up with in 1942. And he based it on the tristimulus functions rather than on the human eye. If Adams had stuck with his original idea of using LMS, then CIELAB, the A star axis, would point to red. That is a tidbit for your next dinner party to casually throw that out and generate some argument among color scientists or pseudo-color scientists. But that's my second tirade. And here is the first part of the computation for A star in the CIELAB system. We see that we have that same cube root function, only in this case it's applied to the X tristimulus value rather than the Y. This is the first part. And here's the second part. We're basically just taking the difference between X and Y. Kind of similar to what was going on in the Elliott Adams paper from 1923, where he's doing the subtraction of the two signals, and then we scale it by some number. On to the third attribute of color, which is called B star in the CIELAB system. B star tells us whether it's yellowish or bluish, which may sound an awful lot like the, what was that called? The color opponent system of Herring. That's the guy. Yes, these are the Herring color opponents, yellow versus blue. If the number is a very high value, if B star is, let's say, 100, then the color is very yellowish. If it's a large negative number, like minus 100, then it's a very bluish color. And somewhere in between, we would say it's gray, or at least it doesn't have any yellowishness or bluishness. B star, the third component of CIELAB. Once again, we have the spreadsheet version of it. If you want it, then give me a call, send me an email, send me a text, stop me on the street, whatever. Here we see the first part of the computation for the B star value. Looks a lot like the other ones. We've got this cube root thing. This is the first part. Here's the second part where we take the difference, just as we did in the atom system from 1923 and also in the his 42 paper. We take the difference between the y and the z, and we multiply that by 200. And that gives us the B star value. The A star and the B star values together help define any position on this plane here. This looks like a color wheel. This is looking at CIELAB space from above. And here we see the A star is perhaps 50, and the B star value is perhaps 50. And this is the coordinates that winds up being. This is Cartesian coordinates, if you happen to remember the analytical geometry that you had in high school. Any point that's on this can be identified by two numbers, and it will be uniquely identified by those two numbers, A star and B star. You may notice that those are just a little bit confusing. We don't normally think in terms of the reddish to greenishness of a color and the yellowish of bluishness. What we think about is the hue. Really, the hue is the important thing, and that's what was brought out in Munsell. Hue, value, and chroma. Hue was very important in the Munsell system, and hue is also important in CIELAB, but it's not a direct thing that's measured. Let me demonstrate that. Here we see that same point, that orange that's over here at like 45 degrees, 50 over and 50 up. Here I have it described in terms of the hue component, which is the angle. In this case, I said 45 degrees. Angle from red. Red is defined as being 0. Actually, it's magenta, but let's just call it red. This vector here is defined as being 0 degrees, and here we move to 45. Yellow is at something like 90. Green is over here at 90 plus 180. That's 180. Down here, this is 270, and then we come from 270 back up to 360, which is the same as 0. Hue is the first part. Chroma is the other part, which is the distance from a neutral gray to the color that you're talking about. In this case, if we have 50 and 50, then this is about 70. Colors can be defined in terms of L star, A star, and B star, or in terms of L star, C star, which is chroma, and HAB, which is the hue. Why did they call it AB, HAB? I don't know. I wish they'd have called it H star, but you could call it that and nobody would get confused. At any rate, you could call the colors in terms of the Cartesian coordinates, A star and B star, or in terms of the, what are they called? Polar coordinates. That's it. I remember now. Polar coordinates, which is the hue and chroma. They're the same, they're different definitions of the same position in color space. Here we see the calculation of chroma. Again, it's in that spreadsheet, fairly easy to do. You may recognize it as being the Pythagorean theorem. And if you don't, that's okay. Here's the definition of how hue angle is computed. And this is, it's got arctangents in it, and there's all kinds of blah, 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 blah. That's in the spreadsheet as well. You don't have to know the math. And there is a bug in this. I should check to see if C star is equal to 0, yada, yada, okay. And now for my third tirade. Tirade is based on a paper that I will be submitting to Color Research and Application. You would think that all colors that have the same CIELAB hue angle, that they would look like they are the same perceptual hue. In other words, you would want the CIELAB color space to reflect how we perceive hues. That would be nice. And if that were the case, then these would all be straight lines. Each one of these lines is from the Munsell color set. This particular line is a bunch of reds. that in this case it is pretty close to linear, but let's look over here in the green. We see that it changes hue rather dramatically. That's not a good thing, because here we have one hue that is the same color, the same hue, and here we have another one. CIELAB tells us something that's wrong about our color vision. They should be all straight lines. Why did that happen? Well, I think I mentioned before that CIELAB is all based on the work of Elliott Quincy Adams from 1942, where he used the tristimulus functions. The tristimulus functions are not the human vision system. They're not the cones. And because of that, we have a problem. If Adams had stuck with LMS, as he had in his 1923 paper, these lines would all be straighter. That's the end of my third tirade. Let me clear something up in terms of the range for A star and B star. I was a little bit cavalier in saying that A star and B star go from minus 100 to positive 100. Well, that sort of statement can be made about L star. It is absolutely true that L star must be between 0 and 100 for any non-fluorescing reflective colors. But that implication that there is a hard and fast boundary for A star and B star, that's kind of not right. I lied. This rather complicated plot tells us what the real range for A star and B star is. If we look at L star equals 95, we're looking at the top of the color space. This little shark fin kind of thing, which is yellow, that's the range for A star and B star. We can't get an A star of 150 at such a lightness, or 100. We can get, though, if we have a very bright color, we can get an we can get a B star that's well over 100. We can't get much in the blue direction, though. Yellow is inherently a lighter color. At the other end here, we have L star equals 5. That's a very, very dark color. We cannot get a yellow, in other words, a B star that's very high there, but we can get the A star and the B star to be, here the A star is very large, above 100, and the B star is below a minus 100. So if you think of this as a topological map, if you think of this maybe as somebody had cut these out of paper and stacked them on top of each other, that's kind of what we have. This is a three-dimensional thingy. Speaking of three-dimensional thingies, I have here a toy that was created by one of my students. Very, very clever here. We see that it kind of has the same shape as the drawing that we looked at before. This slice here, this is the highest L star, and we see that it goes very yellow. And below that, we see the next lower L star. I think maybe this is an 80, and we see all of the other ones in between here. Isn't that cool? I wish I could hand this to you right now so you could have a closer look at it. Something interesting about this, the white pieces of plastic here, that represents the total range of possible colors. And the colors in here that are on the inside are accurate. Those are the colors that actually can be produced with printing. So we see that printing does not cover the whole gamut of colors that are producible. With cyan, magenta, yellow, and black, we cannot reach all of the colors that are possible. Let me introduce the next section here. This next section is the driving force behind the creation of CIELAB. Tolerancing of color. In other words, the company that's buying the print buyer, has specified this is the color that I want, L star of 50, A star of 12, B star of minus 17, whatever those values are. Now, that goes to production, and needless to say, we're not always going to get exactly that color. We're probably not going to get that color. We're very unlikely to get exactly that color. There are certain tolerances that are necessary in any manufacturing process, and color is certainly fits that. So we need to be able to set up a contract between the print buyer and the print maker. We need to set up a contract that says what is acceptable, what is a close enough color. And that's where the tolerancing comes in. The question to ask is, what is the distance between two colors? Here I have two colors. This one is a reddish orange and this one is a yellowish orange. They are some distance apart. Now, if you picture this, if color space were a three-dimensional thing, then I could take out a tape measure and I could physically measure the distance between those two colors. Instead, I can do it mathematically. Does anybody recognize the Pythagorean theorem? Oh, here we have that statement of the theorem in 3 dimensions. We take the difference in A star, we take the difference in B star, and we get the, what do they call that? The hypotenuse of the triangle, which fits this, and here we add in the L star as well. They call that the delta E. The delta E is the distance between two colors. Let me make a clarification here. I kind of messed up in saying A and A star. Technically, the axis is the A star axis and the B star axis and the L star axis, which is such a pain to have to say those and to think of all the ink that has been wasted in printing those asterisks. Why do we do that? Well, there's a fellow by the name of Hunter that came up with a color space of his own. There have been a lot of color spaces. Anyway, this guy Hunter came up with one, and he called the attributes of his color space L, A, and B. So basically those terms were already taken. So we have to call them something different to avoid confusion with the Hunter space, which there are certain segments of the color market that do use LAB rather than L star, A star, B star. So we have to be careful. Within the print industry, nobody uses Hunter Lab anymore. I don't know if anybody ever did use Hunter Lab. So if you say LAB, people will understand what you mean, and only the real pedantic color scientists will call you out on it. Color differences are measured in terms of delta E. That is the unit, like you say 5 inches, you would say 5 delta E. These colors are 5 inches apart. These colors are 5 delta E apart. It's pronounced delta E. Delta is the Greek letter, corresponds to D, and it's used by engineers to refer to a difference, hence color difference. And where did the capital E come from? Well, the word sensation in German is die Empfindung. And I have no idea whether I'm pronouncing that correctly. I probably am pronouncing it wrong, but the word is sensation, feeling, or impression. And that's the term that's used here. E stands for Empfindung, and so this is really the difference in perception or sensation. I think it's funny that we use a Greek letter and a German term together to make that. The intent when they came up with CIELAB back in 1976, the intent was to make it designed so that 1 delta E in any direction is the smallest perceptible color difference. And so you would have a sphere around any point. Every point on that sphere is exactly 1 delta E from that color. And anything within that sphere is something that you cannot tell the difference between the colors. So that would be a very reasonable way to set tolerances. Unfortunately, the whole idea behind that didn't really work all that well. Still, we can make some generalizations about color difference. A delta E is a measure of color difference. It's useful for setting tolerances. And 1 delta E is pretty small, kind of like a just noticeable difference. Delta E of 10 is fairly large. Well, moderate. It means you're talking about a different color. You would probably give it a different name. And 100 delta E is like way big. The difference between pure white and pure black is 100 delta E. Ideally, a color difference of 1 should be a just noticeable difference in color. But unfortunately, a delta E of 5 in the direction of a saturated yellow is close to that just noticeable difference here. So here we have a yellow that has a B star of, I don't know, we'll call it 90, and the one above it is 95. So that's 5 delta E, and if my drawing were correct colorimetrically, then these two colors would be very close together. 5 delta E. So in this particular color and in this particular direction of color difference, we have a factor of 5. So if I were to put a tolerance on yellow, I would say 5 is acceptable, maybe something even slightly large of that in terms of moving in this direction. But a half a delta E, 0.5 delta E difference around gray is a just noticeable difference. If I move from gray to a yellowish, if I move toward red, if I move toward blue, if I move toward green, half a delta E is a reasonable thing for tolerance. If I gave 5 delta E of tolerance around gray, then the colors would be too far off. I said that delta E was figured out in 1976, same year that, along with the same standard of L star, A star, B star was developed in 1976. It wasn't long before people started looking at it and saying it doesn't work well. Roderick McDonald was one of these people in 1978. He worked for J&P Coats, which is a thread manufacturer. Now, thread, if you think about it, the color of thread is very important. You want the thread to match the fabric that you're putting it on. So they were very interested in keeping tight tolerances on their thread colors. He had thousands of pass-fail assessments of experts, people who were hired to do nothing more all day than to sit and look at the thread and decide whether the colors were close enough. So he had those assessments. He had measurements of all those colors and the assessment of the color experts. And he saw that CIELAB delta E did not correlate that well with when people said pass or fail. But he did see a pattern to the disagreement. It wasn't just that the numbers were all over the place. He saw that basically what I showed, that yellow in the B star direction had a very wide tolerance range, and toward gray it was much smaller. Let me explain the difference between a delta E tolerance. Here we see in the blue circle, we see this is the delta E tolerance of some number. It's a circle around this point in the center. And the greenish thing, that ellipse, is the pass-fail line. In other words, this is where the color experts decided anything outside of this ellipse was out of tolerance, anything within that is in tolerance. So there we have a number of different conditions that could happen. In the very center here, this kind of seafoam green, both the computer and the color tolerance person agree. They say anything in this range is a good color, a good match. Anything in this outside range, this AEcmc area, both the computing delta E, and the color tolerance expert would say that the color is outside of tolerance. Now we get into the interesting ones. Here we see this region here. The human says this is good, and the computer, using delta E, says it's bad. Now that's going to cause some problems, particularly with the thread manufacturer, because they're going to say, look, this thread is the right color, but the computer's going to disagree with them. Okay, so that's an unhappy condition. We also have the opposite condition here, this region here and here. The human says that they're bad. They're outside of that ellipse that says that the colors are okay. So the human observer looked at that and said, no, this thread does not match. This is a bad match. But the computer with the circle says the tolerance is good. We are within tolerance. Now, that's perhaps going to make the thread dyer happy because here we're getting away with having bad product, to put those in very black and white terms, no pun intended. But it's the thread buyer is going to be unhappy with that because they're going to look at the thread. They're going to say, I don't care if it's in tolerance according to delta E. My eye tells me that it's out of tolerance. The thing is that the tolerance region is not a circle. It's an ellipsoid. And I say ellipsoid is a three-dimensional ellipse. And it's oriented toward gray. The major axis of this ellipse is pointed toward the center here. This is what Roderick McDonald had noticed in 1978. There are three characteristics that define this ellipse. The first one is the hue angle, how that's oriented. There is the difference in chroma, which is the major axis here, going along this blue line. That's the difference in the C star value. And this red line, this red arrow, tells us the difference in the hue angle. If you identify those three things, hue angle, difference in hue angle, and the difference in chroma, you have fully characterized an ellipse. Now, there's more characterizations if we are defining the ellipsoid, but it's easier to think about this in 2 dimensions. So we have the orientation angle. The ellipses have a length to them. The ellipses have a width to them. So his idea was to take the original equation for delta E, which is simply the Pythagorean theorem, and do some scaling on it. He would compute the hue, the difference in hue, and he would scale it. He's allowing perhaps a little less, a little bit more. He'd also scale the difference in chroma. And with that formula, which is a little bit ugly, but okay, he came up with what is known as delta E, the color difference, JPC, J.P. Coates, 1979. He started this work in 1978. He published it in 79, and hence we have a different formula for computing the color difference, which is always a good thing. It's always great to have more than one formula. This was introduced to the Color Measurement Committee of the Society of Dyers and Colorists. This is a committee. The Society of Dyers and Colorists is still around. The Color Measurement Committee is no longer around. They were known as CMC, the Color Measurement Committee. So Roderick McDonald took this to that committee and said, I think maybe we should adopt this as a standard. And they modified a little bit, and they developed in 1984 something called Delta E CMC for Color Measurement Committee. So the wonderful thing is that now we have delta E, which is the 1976 formula. We have delta E JPC 79, which is a variation on that. And we have delta E CMC, which is a variation on that. Delta E CMC from 1984 is still in use today for color tolerancing. And either to avoid confusion or to create more confusion, the original one is now known as delta E AB. And I have no idea why they decided to call it AB. I think it would have made more sense to call it delta E 76. That's not one of my tirades, though, because that's not all that important. Anyway, we call them delta E AB, delta E CMC, delta E JPC 79, which nobody uses anymore, so let's forget about that one. Here we see what the delta E CMC tolerance ellipses look like. We see that, as I predicted before, with the yellow, the ellipse is elongated this way. So we're allowed a larger difference in B star than we are in the other directions. We also notice that the circles We go from ellipses down to circles in the center. The ellipses get less eccentric. They get more circular as we go down close to gray, and they get smaller. So the tolerance around gray here is fairly small in terms of A star and B star. We also notice that the difference in chroma, here we see it's fairly wide. It's getting fairly narrow here at yellow. We can tolerate a somewhat larger difference in A star, B star, and hue angle than we can over here in orange. It gets big again around red and bigger here. This is perhaps the widest. This is over near cyan. Now for my fourth tirade. Are you getting tired of these? My opinion is that the CMC color difference formula is a pimple on a wart. The wart is the CIELAB formula that doesn't quite work quite right. And the pimple on it is the decision, rather than to fix CIELAB, the decision was made by Roderick McDonald and carried on from there. The decision was made to fix the color difference formula, not use the simple formula that we all know, the Pythagorean theorem. Rather than use that, he adjusted the formula for taking the difference. In other words, Roderick McDonald and future work with the CMC, etc., it fixes the symptom and not the problem. Rather than adjust the color differences as they did, why not fix the darn color space to make CIELAB work better? Oh, I'm glad I got that off my chest. Roderick McDonald and the work of the CMC, that does not represent all of the work that's been done on delta E to try to make it work better, to better fit the data that has been collected on people doing tolerancing. Here we see delta EAB, the 79 formula, the 84 CMC formula. BFD stands for not what you might think. It stands for Bradford, which is a college in England, 1987. CIE 94. CIE is the official committee that does all this stuff that has to do with color. They came out with an official version in 1976. They came out with a modification in 1994. LCD is another one, somebody's graduate thesis. DIN, which is the German Deutsches Industrie Normen Schligenschlagen Fliegenflagen. DIN 99 is leads to a color space that gives us delta E 99. And finally, the CIE got involved again in 2000 and created a different version from this. The wonderful thing about standards is there's so many to choose from, which causes a problem in our industry. A lot of people are still using delta E76, the delta EAB. I have a red arrow here to show don't do that. That's a bad idea, and your tolerances will have to change with every color, or you'll, it's just icky. Don't do that. A lot of people are using delta ECMC, probably because it has grandfathered in. They started on it early because they saw that color differences weren't working well. So particularly in packaging, you see a lot of delta E76 CMC. And that's not so bad. It actually works a lot better than delta E76. The official ISO standards today require that, and this is in the print industry as well as every other industry, if you're going to follow the CIE standards, which is part of the ISO standards, if you're going to follow the ISO standards, then thou shalt use delta E00, delta E2000. This is actually not one of my tirades. I have a couple of blogs that I wrote about the delta E equation. You can look these up. These notes have been, the lecture slides have been uploaded to Canvas, so you can have a look at these and read them. They are very entertaining, I'm sure. Now we come to my fifth and last tirade, at least for this lecture. The delta E2000 formula is defined in this document from the CIE 142, Improvement to Industrial Color Difference Evaluation. The delta E formula delta E 2000, was voted the ugliest equation in the history of the known universe. And it probably is the ugliest in many of the multiverses that we are unaware of. Here's the first part of it. We start off with that L star, A star, B star stuff that's already just a little bit ugly, and then we change it a little bit. This part of it here with the raising the chroma to the 7th power and dividing it by, okay, no self-respecting mathematician would ever just raise something to the 7th power. That's like, gosh darn silly. And then there's this other stuff. This is actually kind of standard stuff, so that's not ugly. Then we get into this. This actually kind of makes sense if you're a mathematician. If you're not a mathematician, this is like really ugly. Okay, I'm just going through the formula here. We'll continue on. I'm not done looking at the formula yet. Then we compute these silly things. Gosh darn it. It's just more numbers all over the place. And then we have this thing with sines or it's all cosines, I guess. Cosine of this and that and that and the other thing. This is kind of a Fourier series thingy, and oh God, you don't want to know about that. And we're not done yet. Then there's another correction factor that they put in for around 275 degrees to tilt things around, and here we have a c to the 7th power again, and this, oh my God, this is getting really ugly. And then we combine them all together to make the delta E formula. The previous formulas allowed us to compute all these factors in here, and then this is more complicated because it's got this term in it, more complicated than the standard delta E formula, the Pythagorean theorem. This has, oh my God. This is so ugly. How ugly is it? This equation is so ugly that there was a paper in Color Research and Application that came out in 2005, 5 years after delta E 2000 was invented, describing how to test this formula. Mere programmers, mere mortals were asked to create this and put this in their software, and there were a lot of discrepancies. People's software would disagree on what the delta E 2000 was, because a lot of people typed in a number wrong someplace, did something wrong, and this fellow, Gaurav Sharma, and the group of people he was working with, came up with a data set that would allow a software person to test whether they got it correct. They put in a bunch of stuff in this test to make sure that they caught all of the stupid little errors, the typos that somebody might make. And for my own part in this, in my years here in color science, that's since 2000, 3 people have sent me spreadsheets and said, John, does this work? Is there a mistake in here someplace? And 2 of those people, 2 out of 3 of the spreadsheets that were given to me to look at by people who are fairly competent, 2 of them had errors in them. I rest my case. This is an ugly formula. It is way uglier than what is justified. They didn't have enough data to put in to get blah, 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 blah. So that's my last tirade. Summary for today. CIELAB. Any questions? Well, actually, CIELAB. CIELAB is the color space that we use to measure color, to communicate color, to decide whether something is in tolerance. It is the way that we use to measure color. So it is critically important. And as much as I pick on things that I don't like about it, it is something that we have to live with. It's there. And to be honest, it works pretty well. Kind of. But I'm predicting, with all of my tirades, I'm predicting that in your lifetime, in your experience with color in the future, there will probably be a change. We will probably change over to something else. And when that happens, you can look back and say, yeah, John told me that. There's 3 attributes in CIELAB, L star, A star, and B star. And we could report L star, C star, and HAB, those three, an equivalent way, and we can compute back and forth between them. If we're given an A star, B star, we can compute the L star, C star, HAB, and vice versa. And the result of CIELAB, the calculations that went into it, is that it looks a lot like Munsell color space, which makes it very useful because a lot of work went into the Munsell color space. But as I said before, it's not perfect. And so ends today's lecture and all of my nasty tirades about CIELAB.